Welcome to Physics 1, Lab 5, Falling Slinky. Alright, so the purpose of this lab is to analyze the motion of a fully stretched slinky as it falls to the ground. So for video analysis, we're going to use Tracker. For simulative model, we're going to use GlowScript. And the goal of this lab is to analyze the motion of the bottom of the slinky and how it acts. The result is that the bottom of the slinky stays in the same location until the slinky is completely compressed to its equilibrium length and then begins to fall all as one mass. So, some physics principles that we need for this lab. We need Newton's second law, we need drag force, and we need gravitation and tension forces. So, the system's change in momentum is proportionate to the net force, so this gives us all of these formulas that we will use in order to calculate things during the lab. That's the net force equals the change in position over the change in time, the change in momentum over the change in time, the change in momentum, the velocity update formula, the position update formula. So, drag force. This is a resistant force that is caused by motion through a fluid. In this case, the fluid is air. So the drag force is going to be equal to negative b times the velocity squared in the direction of the velocity. So in this case, b is just a proportionality constant that is found through trial and error. Gravitation and tension forces. So in this case, the slinky force is the tension force, and we are on the surface of Earth, so there's going to be gravitation. In this case, the slinky force directly counteracts the force of the gravity. So we have the force of gravity, which is just negative mg in the y direction, and the force of the slinky, which is just the opposite of that, which is mg in the y direction. So for our tracker analysis, here you can see on the left the actual video that we're using, the source video. So it stated in the video that this guy is 1.75 meters tall, so that's the scale of the video, and it states that the slinky's mass is 0.218 kilograms, and this also gives us our original position and our original velocity, because we know that it starts at rest. So using these initial values, we can plug them into our GlowScript model. So we have the system's mass in kilograms, we have the position in meters, we have the time, and we have the gravitational constant, and we also have the j hat in this case, which is just the unit vector for the positive y-axis, and the proportionality constant, which ended up being 75. So for our first loop, this is going to be during when the slinky is not actively falling. The bottom of the slinky is staying stationary and staying in the same position. So in this case, we still have the force of the slinky, which is exactly equal to the negative of the force of gravity, which is negative times the mass of the ball times g times j hat. And here we just have the momentum principle and just advancing the clock. For the second loop, this is going to be when the tension force is no longer there. There's no more pulling up on the slinky. Instead, it's all of just motion down towards the ground, all as one mass. And here we include drag because we know it's going to move. So here are the results. So on the left, you can see our observed motion versus on the right, you can see the simulated motion. This is actually quite accurate. The simulation did quite a good job here. As you can see, as we progress through time, the tracker data is a little bit inaccurate, most likely to point mass positioning errors, so human error when I did that. Versus the simulated version is obviously going to be very consistent as it does it through a computer. So, but yeah, so as you can see, they both stay constant for a long time, and then once they reach to a point where the mass is all in one location, then it starts to fall. So, some possible errors. As I said, error number one, my tracker placement could be off, and it probably was a little bit off in multiple locations. In fact, we just saw that. And the error number two is that there's wind and the movement of his hand. So these are things that could have acted to mess up the observed model that we had as he drops the slinky. Why does the bottom of the slinky not move? So the bottom of the slinky doesn't move because the slinky's tension force cancels out the force of gravity directly until the moment that the slinky acts as one mass. When it acts as one mass, it all falls using gravitation just towards the center of the Earth. So in this case, the slinky acts as a spring pulling up in the straight line in the y direction. What if there was an additional weight on the bottom? Would the slinky still remain stationary? So the answer is yes. If the slinky was strong enough, if it had a strong enough tension force to support the entire system, so the entire system being both the weight and the slinky, then the answer would be yes. If the weight was too much, if the force of gravity was too much, then it would begin to pull down before. It would just pull the entire mass system down. Thank you.